Have you ever tried opening a sealed bottle after it's been sitting in the sun? That sudden hiss when you twist the cup? That's pressure, and it's not just heat doing the work. There's a hidden rule behind it. It's called Lussac'S law. In the early 1800s, a French scientist named Joseph Louis Gay-Lussac made an important discovery about how gases behave. He was born in 1778 in a small town called Saint-Léonard-de-Noblat in France. Later, he studied at the prestigious École Polytechnique in Paris, where he focused on chemistry and physics. While studying how gases behaved under different conditions, Gay-Lussac discovered a fascinating pattern. When the volume of a gas remains constant, its pressure increases as the temperature rises and decreases when the temperature drops. This relationship became known as Gay-Lussac's law. It gave scientists a deeper understanding of how heat and pressure interact, and it remains one of the key principles in gas behavior today. We will be doing the candle jar experiment. The materials we need are and that's all we needed. Let's start. Pour water into the dish. Add food coloring for better visibility. Place the candle upright in the center of the dish. Then, light it. Carefully cover the candle with a glass. After a short time, the candle flame goes out and the water level rises inside the jar. How does this demonstrate Gay-Lussac's law? When the jar is placed over the candle, the flame heats the air inside. When gas molecules are heated, they move faster and spread out, heating the inside of the jar more often and with more force. This causes the air pressure to increase inside the jar. As soon as you cover the candle with the jar, the space becomes sealed. No new air can come in, so the amount of gas stays the same. The heated air expands and the pressure inside the jar becomes higher than outside. However, as the flame goes out due to a lack of oxygen, the air inside the jar begins to cool. The temperature drops and so does the pressure. The lower pressure inside the jar creates a vacuum effect, causing the water from the outside to rise into the jar. Hello everyone! Today we will be solving a Gay-Lussac's problem. So, what are the materials we need? First is a calculator to solve it. Next is a pen to write the answer. So, let's start. A sealed container of gas has a pressure of 300 kPa at a temperature of 27 degrees Celsius. If the temperature is increased to 127 degrees Celsius, what will be the new pressure? So we have a given of 300 kPa, but we have a 27 degrees Celsius. So we need to convert it into Kelvin. So how? All we need to do is to add it into 273 K. So 27 plus 273 K is 300 K. And 127 plus 273 Kelvin is 400 K. So now we can solve it. However, the unknown here is P2, which is the final pressure. So we have a given of initial pressure, initial temperature, final temperature, but we don't have the final pressure. So let's apply the Gay-Lussac's law. So the formula is P1 over T1 is equals to P2 over T2. So we have to find the formula in finding the final pressure. So all we need to do is cross multiply it. So first, let's write P1 over T1 is equals to P2 over T2. So we have to cross multiply it so we can find the formula of the final pressure. So cross multiply. So it will be P1 over T2 is equals to T1 over P2. So we will be finding the final pressure. So let's divide this to, so we will be finding the final pressure. So let's divide it to T1. So it will be cancelled T1. So now we have the formula in finding the final pressure. So P2 is equals to P1 over T2 divided by T1. Next is, let's substitute the values. So we have P2. So the P1 we have is 300 kPa. 300 kPa times T2, which is 400 K, divided by 300 K. Now, let's multiply it and solve it sa calculator. So, 300 times 400 divided by 300 is equals to So here, let's divide it. 300 times 400 divided by 300 is equals to 400. So let's consider the significant figures. How many the least significant figures? So here, 300 only 1. And the T1 is also a 1. And the T2 is also 1. So therefore, we need to find an answer that will have a 1 significant figure. So the answer is 400. So it's already 1 significant figure. So let's put 400. Cancel the K. We have kPa. So therefore, if the temperature is increased to 127 degrees Celsius, the new pressure will be 400 kPa. And that's all. That's how we apply the Gay-Lussac's law. So, as you notice, as you observed, while the pressure increases, the temperature also increases. So as you can see, the final temperature here is 400 K. So our final pressure also is 400 kPa. So the relationship of pressure and temperature is directly proportional at its constant volume. And that's all.